Hey guys, what's going on? I'm back at you here with day 46. Today we're going to switch gears a little bit from our Riemann sums, approximations of definite integrals, to talk about indefinite integrals. So again, one way we think about integrals is the area under the curve, right? And we estimated that area under the curve of definite integrals by using left and right Riemann sums, midpoint Riemann sums, and trapezoidal sums. I also had you find the exact area when we had shapes like triangles and rectangles and stuff like that. Today we're looking at indefinite integrals, which is another way we want to think about integrals. We want to think about integrals as anti-derivatives, right? The opposite of a derivative. So to start here, I want to show you just a little quick review. Okay, so let's go back to derivatives really quick. Let's take a look at these two derivatives. Go ahead and solve them out. What do you know about the answer to these two derivatives? Well, taking a look at the first one, right, the derivative of 4x cubed, remember how we operate our power rule. We multiply the exponent. 3 times 4, we're going to get 12. X, and then we have to reduce the power by 1, so we get 12x squared. Interestingly enough, with this other derivative, we also get 12x squared. When we do the derivative, right, 4x cubed is the derivative is 12x squared, but that plus 2, right, that's a constant. The derivative of a constant always equals 0, so we get 12x squared. So we get this idea about two different functions, when we do the derivative, give us the same answer. Now, when we do derivatives, right, we know that anytime we do the derivative of a constant, we get 0. Okay, we're going to have to account for that fact when we do antiderivatives. When we go backwards, we have to account for the fact that we don't know, right? If I ask you to do the antiderivative of 12x squared, I don't know if it's going to be 4x cubed, or 4x cubed plus 2, or 4x cubed plus 100, or 4x cubed minus pi. There could be any constant added or subtracted at the end of that antiderivative. So let's just do a simple one here that the answer should be very obvious to just kind of ease you into this. We're going to have a problem that looks like this. So we can tell that this is an antiderivative because on the big S here, the integral sign, notice there's no number on top or bottom, right? It's just the integral sign by itself. That gives us the idea that this is an indefinite integral, okay? And we know, one way that we can think about antiderivatives is what function gives a derivative of 12x squared? Well, it's pretty obvious because it was in the, the review problems here. The antiderivative of 12x squared is 4x cubed. We have to account for the fact that there could be a constant added to the end of that. So what we say is we say at the end plus c. I just add a plus c. Something to notice when we're working with polynomials, when we do a derivative, notice that the power always drops by 1, right? If we derive something that is x cubed, it shows up as x squared. If I had x to the 5th, I know my derivative is going to have x to the 4th. So when we do antiderivatives, we know that the power should increase by 1. So let's take a look at how this works. So when we take a look at this, right, there's going to be a kind of a shortcut coming soon. When we take a look at this, I want to think about, okay, I know that my derivative or my antiderivative here is going to be something to the 3rd power. I know it's going to be something to the 3rd power. Well, what coefficient do I need to put out front so that it ends up being 6x squared? Well, again, I have to if I was doing the derivative, I'd take 3 and multiply by the coefficient. So I have to think 3 times what equals 6? Well, that's pretty obviously 2. Again, I have to account for that possible constant, so we'll call it plus c. But what about this problem? Okay. Well, again, I'm doing an antiderivative. So my power should be increasing by 1. So I know it's going to be x to the 7th. But I think, what coefficient should I have? So when I multiply by 7, I get 8. Ugh. It's not an integer, right? If it was a 1, I'd get 7x to the 6th. If it was a 2, I'd get 14x to the 6th. So I realize that it's going to be a fraction here. 7 times blank equals 8. Well, I can think about, well, maybe I'll make it I have to make it a fraction, right? Maybe I'll put the 8 on top and the 7 on the bottom. If I do that, now when I multiply 7 times 8/7, the 7s would cancel and I'll get 8x to the 6th. Again, I got my plus c. But I don't want to have to play that guessing game all the time. So I want to come up with a rule here that can work. Okay, when I take a look at this, this 2 could have been written as 6/3. Right? I take my original coefficient and divide by my new power. Again, I take my original coefficient and I divide by my new power. I call this method bump and divide. Okay, it's our power rule of integration. Okay, and I call it bump and divide. I don't call it divide and bump. I call it bump and divide. So what I do here is I bump my power by 1 and then divide by that new power. So if I have something like this, here's what I tell myself. I'm going to bump the power and divide by my new power. Now, you can always test. Sorry, there should be an equal sign there. You can always test your antiderivative to see if it's correct by doing the derivative of your answer, right? Just like when you learn to subtract, right, you could check it by doing addition. Same idea here, right? So if I do the derivative of this 7x, 7/3 x cubed, if I derive it, I'm going to have 3 times 7/3 x squared. My 3's are going to cancel, and I'm going to be left with 7x squared, which is what I started with here. Okay? It's always a good idea, right, especially as we're learning this, to do a little check to make sure that your antiderivative is correct. Now, let's write a rule here in terms of a's and n's, so it's a little bit more generalized. So what if I was going to do the antiderivative of ax to the n power? Okay, so I'm just having general terms a and n. So again, what I have to do here is bump the power by 1. Right? 6 went to 7. 20 goes to 21. N goes to n plus 1. Okay, and what I have to do is I have to take my original coefficient, that a, and divide by my new power. I'm not dividing by n, I'm dividing by the new power, n plus 1. So the coefficient should be a over n plus 1. And then again, I have to tack on my plus c because it's an indefinite integral. There could be a constant of any kind attached there. Now this rule works for all n values except for one n value. There's only one n value that it doesn't work for. And take a look at that coefficient, a over n plus 1. What number are we never allowed to divide by? Well, we can't divide by 0. What would n have to be so that we would be dividing by 0? Well, n would have to be -1. So this works for everything except n cannot equal -1. We'll talk about what happens if our n power is a negative one. We'll deal with that in another video down the line. Okay, so let's do some examples. Okay, so I have the antiderivative, right, the indefinite integral of -5x squared dx. Again, I'm going to bump my power. Go ahead and try it on your own first. Okay, but I'm going to bump my power and divide by my new power. So I'm going to have -5 over 3 plus c. Again, if I did that derivative there, -5/3 x cubed, right, when I do the derivative, I'd take that 3 and multiply it. Well, the 3's are going to cancel to make it -5x squared. The plus c goes away when I do the derivative, and I get -5x squared. Example 2. Okay, I am going to, again, bump and divide. Try it on your own. So I'm going to bump the power to x to the 4th. And I'm going to divide my coefficient 8 by my new power 4, 8 over 4. Okay. Now, when you see that it simplifies, go ahead and simplify it. I know 8 divided by 4 is 2. So I'm going to get 2x to the 4th plus c. Again, the derivative of 2x to the 4th is 8x cubed. So I know it's right. Okay, let's try this one. Uh-oh. Well, you knew I'd do something like this, right? Well, how did we deal with doing the derivative of stuff like this in the past? Well, sometimes we had to rewrite it so it was an ax to the n form. We're going to do the same idea here. So before I actually do my before I bump and divide, do my antiderivative, I want to rewrite this thing as ax to the n form. So I'm going to take that x squared and I'm going to move it up to the numerator with the 4. And when I do that, I'm going to have to change my power from 2 to negative 2. Notice how I didn't bump and divide. All I did was rewrite. So notice that the big S stays. The big S stays until I actually perform my antiderivative. That's just rewriting, so the S needs to stay. Now I'm ready to bump and divide. So I'm going to bump my power by 1. Be careful here. When you add 1 to negative 2, you actually get negative 1. And whenever I write this, I leave myself some space here for my coefficients. And now I have to do 4 divided by my new exponent. My new exponent is negative 1. So I have to do 4 divided by negative 1. In my head, that's going to reduce to negative 4. And again, do the derivative to make sure it works. The derivative, I'd take negative 1 times negative 4 to get positive 4. X to the negative 2, which is the same thing as 4 over x squared. All right, one more example for you. Once again, this isn't an ax to the n form. So I want to rewrite this thing so it's an ax to the n form. And I have to tell myself square root means what in terms of an exponent? Well, square root means to the half power. So I want to rewrite this thing as 9x to the half. But remember, when I rewrite it, I'm not doing the antiderivative yet, so I need to keep my big S. And now I just need to bump and divide. Now I have to deal with fractions again, okay, but you can do it. I have to add 1 to a half. Half plus 1, right? If you don't see that it's 3 halves, that's okay. Just think of it as half plus 1. That's like 1 over 1. Get a common denominator. And we get 3 over 2. So my new power is x to the 3 over 2. Now I have to do 9 divided by 3 halves. And once again, we're going to channel our inner grade school math selves. So whenever I divide by a fraction, I prefer to multiply by a reciprocal. So instead of dividing by 3 halves, I'm going to multiply by the reciprocal, right? In case you don't see that, here's what I'm talking about. 9 divided by 3 halves is the same as 9 times the reciprocal 2/3. So I'm going to have 2/3 times 9. Again, plus c. Well, 2/3 times 9, I'm going to cross cancel here. This is going to be a 1. This is going to be a 3. And I'm going to end up with 6x to the 3 halves plus c. And again, on these trickier ones, I like to actually do the derivative to make sure it works. 3 halves times 6 would be 18 halves, or 9x to the 1 half. 9x to the 1 half, 9 root x. So it works. All right, that's it for today. And we'll see some of these practice problems tomorrow. Talk to you guys later. 2 chains. Bye.